you guys remember that we had a problem having this equation that wasn't quite right. So what happened is we're looking at the equivalent circuit and say, well, that's VGS equal to, because when we short the circuit over here at the input, we have VGS over here, but this is the ground. And what we're saying, there's a current flowing here, so there's a voltage drop over here. So this voltage is apparently the reverse of this voltage. And what we found was VGS equal to minus GM times VGS times RS. Because this current is related to VGS. Now this equation actually is not possible. So if you look at this equation here, it is actually not possible because you have VGS on both sides, and because GM and RS are not zero, but they are also not one, most likely. So therefore, the only possibility that equation is correct, the only condition this equation valid would be VGS equal to 0. But of course, if you go back to the circuit, you can look at it. Well, this is the ground and this is the ground, and you're going from ground to ground, and then you have sort of voltage drop over here, and you have voltage drop here. So therefore, the whole loop has 0 voltage. So therefore, you can conclude pretty much, yes, VGS has to be 0. So similarly here from this equation that we have to say VGS is absolutely has to be 0. So if VGS if VGS 0, then basically what happens? If VGS 0, which means this current is 0, right? The VGS times GM. So this 0 means this current source is open. If that is open, so when we look at this way, what do you have? So but this is open, so VO over IO is actually RD. So therefore, we conclude that RO is equal to RD. So that was a little bit hiccups over there that try to figure out. Okay. And then we went through the CE amplifier with RE, and we went through the process. So today we're going to cover 2 more amplifiers. One of them is common gate, and the other one is well, common gate and common base are the same or similar at least. And then we're going to go over also to emitter follower and a source follower. So those, then we cover all 6 types of amplifiers. And if we have more time, then we'll go into a little bit about DC biasing. And then next week we'll talk the last section of the chapter is the actual amplifier that you will see in real life, where you have this biasing, then you have capacitors for bypassing low frequency signals and things like that. So as I said before, next Tuesday, we are having guest lecture, and then Thursday we are going to do some sort of a recap and some examples of this chapter. Okay, because we're only testing this chapter, so we will not go back to the previous chapters. So by looking at a common gate amplifier, by its name, the gate is grounded. So the gate has a common ground as the input. So input and gate share the common ground. So this is called common gate. So if a gate is grounded, the input is typically connected at the source. So this is just sort of configuration. So if a gate is connected to source, apparently, again, I've mentioned many times that for circuit like this, we actually neglected the DC voltage. So this is kind of a small signal model already. It's just we didn't draw the DC voltage. If you draw the DC voltage, and it will be here, like RD is connected with DC. But for small signal, VDC is ground, so RD is connected to ground. So you kind of gradually get used to this type of drawings. It just represents the small signal, neglecting all the DC variables or DC parameters. So for this one, because there's something at the source, so therefore the best way is to use a T model. Now again, you can use pi model. There's nothing wrong with that. It's just the process of deriving the gain and the input resistance and output resistance becomes a little bit more complex, right? So in this case, we're going to use the T model. Remember when we talk about small signal models, what we always do is we go find where the transistor is. And once you find the transistor, you would draw the model like, okay, so the T model look like this. Or sometimes we simply use the I to in place of that. And so this is your model. So your model top is your D, and bottom is your S, and this is your G. So given that, now you find the model, now we look at what are the things connected onto each of these terminals. So if you look at gate, apparently in this case, gate is grounded, so we'll simply ground it. And the source, we have what is connected. The source, you look at the picture on the left side. We have RSIG with the resistance of the source and we SIG. So we will connect that to okay, so now we complete the connection as a source. So the next we're going to look at the drain. It's very simple. In this case, the drain only has RD connected. So we're going to connect this drain RD to ground. And sometimes you also have a RL connected as the output. Excuse me. But that's not going to change too much because when you have RL connected, RL and RD are going to be in parallel. And sometimes we also have RO, which is early resistance. And when you have that, all three resistance become in parallel. So it doesn't change the whole picture. Only the value actually change a little bit. Our load resistance. Yeah. So, if I go back to the original circuit, often what it looks like, the real circuit will look like this. So the real circuit look like this at the bottom. So you have VDD connected to VDD, drain connect to VDD and source connect to the load and gate is grounded, and you have RL. Often what I'm saying that sometimes we have like RL connected over here, and we also have sometimes we have RO, which is the resistance connected also. But if that's the case, it changes a little bit. But over here, we're gonna just have RL connected, RT connected. So we're gonna have. All right. So this is the circuit that we have. Now at the so typically what we want to do is we want to find three things. One is the gain, and another one is input resistance. The last one is output resistance. And the gain is defined as VO over VSIG. And our in and our out is defined as, we're going to talk to that a little bit later. It's typically, let me see, have a space, yeah. So when you have this circuit like this, and if you inspect VO, what VO is going to be? So VO is, like in this case, sometimes it's easy to do it like this. If we define a current I, so to find a VO, you can say that VO is going to be. Let me redraw the circuit over here so we get a better derivation over here. This RS more often can be just written as 1 over GM. So let's do one. So we can see that VO is going to be minus I times RL, right? So your VO, because current flowing up, so VO is I times RL, all equal to GM times VGS times, so let's call this RD.
Can it be from, say it was RD?
RD, yeah, sorry. I'm often that. GM times VGS times RD, same thing, okay? The next, we need to figure out what is I, or what is VGS. Either way, you can figure it out. So the second step, if we use I, we need to figure out I. Now, in order to figure out I, we can look at the circuit, this loop. Guys, look at this loop from gate to source. They are both ground, right? So actually, this is a little loop over here. So which means from ground to ground, you actually form a perfect loop, right? Even though you look at it sometimes, when we do circuit analysis, we always had an actual loop. You always have components end-to-end connect. But in electronics, we often just have a common ground. We don't have an actual line connect loop anymore. But you can imagine your brain saying, well, there's a ground here, so there's a ground here. So actually, I can connect these two ground together. So what does it do? It forms a perfect loop. So within that loop, we can now, for example, I just, for the easy way, I just connect like this, right? So it becomes a loop. So for that loop, we have one voltage source and two resistors. So what we're saying is that, well, if we find the current in this branch, we have loop is VSIG equal to, actually, if you look at this way, the voltage would go up in here. Does it make sense? Because if this is positive and this is negative, the voltage would go up this way. So how much is the current? Which is this voltage divided by the two resistors, right? So the whole voltage source is dropped on those two resistors in series. So what we're saying is I equal to SIG. Let's call this I. The up one we call it ID. Now we call it I, so it should be fine. So equal to RSIG plus 1 over GM. So from here, we can see ID equal to minus I, because ID was defined okay, this is clear. So ID is bottom, so ID is actually equal to minus I. So therefore, we can plug in this one to minus SIG over R SIG plus 1 over GM. Yeah, so we're going to plug in this one back to this equation over here. So we got O equal to minus now becomes plus. So the two signs are going to cancel. We have SIG over RSIG plus 1 over GM times RD. So from here, we can find AV equal to VO over SIG equal to RD over RSIG plus 1 over GM. So we find the gain to be very simple. So in this, you can see why T-model is simpler in this case, because we didn't involve VGS at all. So we simply find the current, because what we wanted is to find the ratio. Once you have the ratio, let's say input is 5 millivolts and your ratio is 100, and the output is like 2500 millivolts, right? So that's how you can get really just very simplified circuit. Now, there's one more thing I just want to recap here. Why ID is minus I over here? Because the gate current is 0. Remember, the gate current is 0. So therefore, I is minus ID. So if this is BJT, this I and ID will not be equal because this IC and IE, there's a difference of IB. Now, of course, you can neglect it and it will be similar, but just in case you understand why this I equal to ID, because gate has 0 current, right? So I just want to mark it down on the circuit. Okay. So we found this gain, right? So next we want to find input and output resistance. To find input resistance, remember what we do is we apply a voltage at the input, and then we find the current, and then we use the voltage divided by current, we get the input resistance. So in this circuit over here, so there's one thing just to be careful is that this SIG is troublesome often because RSIG is the internal resistance of the source. So ideally, RSIG is not part of the amplifier, right? Because if you replace the input with a different source, this RSIG will change. So therefore, when you calculate the input resistance, often what you do is you don't include this one. Okay. If you don't include this one, what happens is that we will simply apply voltage over here, and we find the current, and then we will find the input resistance. So by doing that, you have an equivalent circuit like this. So we're going to have an equivalent circuit. Let's use the VI. So we'll find the current up here. So by looking at this, you guys can tell me what is the current over here? We'll call it II. By looking at the bottom circuit, would you be able to find the current? Because this is ground and this is ground. Current going up here, this is a perfect loop. How much is the current? VI by R by 1 over GM, right? So what we're saying is, where's my pen? Oh, over here. So II equal to VSIG over 1 over GM. Let's do it this way. OVI, right? And then our definition of Rin is VI over II, so equal to 1 over GM. So this is kind of very simple. I think if you read the book will say, by inspect the circuit, we find the input resistance 1 over GM. Sometimes you get confused. How do I inspect? It's actually It is inspection because if you look at this loop over here, yeah, so this one voltage source applied to one resistance goes to ground. So therefore the resistance actually calculated, okay? So now the next step, we're going to look at output resistance. To find the output resistance, what we're going to do is we're going to apply a voltage at the output and find the current. So, but also, of course, we short. Now, this also very important is that because, as I said, this RSIG is part of the input voltage. So we're going to short the whole thing over here. Now, if you only short the voltage source, you can get a different output resistance that will include RSIG. But the problem is that when you replace this source with a different source, the output resistance actually changes. So that's the difference. But in the book, it actually confuses. If you read the book, and you will find that sometimes it includes RSIG, sometimes it doesn't. So personally, I would prefer that you don't include RSIG because that is your source, not part of the amplifier. When we talk about output resistance, we are talking about the output resistance of the amplifier. So we should short the whole thing over here, okay? So we're going to short this to ground. So, but in this case, actually, it doesn't really matter very much because you're going to see it's only works when we have the emitter follower that makes the difference. But in this case, it actually doesn't matter very much. But let's see. So we're going to short the whole thing to ground, but the gate is also ground. Wow, doesn't look good. Let me do it a second. Okay, so the circuit over here is what I'm doing is I'm going to short the voltage over here. As I said, I'm also shorting the RSIG. I'm only leaving 1 over GM over here. The gate is also grounded. So by this time, you probably notice that this resistance is from here to ground, and this resistance is also from this to ground. So what do you have here? A zero resistance in parallel with the resistance. What do you get? A zero. Basically, this is the ground. And also, there's no voltage source in this loop. So therefore, there's no current because you have ground to ground. The resistance is connected between ground to ground, so there's no current. If there's no current, what happens to this current? This is open circuit. If this is open circuit, what do you have for the current? So basically, what we're saying is we only have.
Wait, so because it has nowhere to go, it just becomes open?
Huh?
Or, oh no, because that's.
So you have VO here, you have RD here, and you have IO. So now, because the current source is open, so therefore you would have only VO connect to RD. So therefore your IO will be VO divided by RO, and your output resistance equal to VO over IO equal to RD. So in this case, your output resistance is simply just RD, and your input resistance is 1 over GM. So that's this common gate amplifier. That's what we get. So for any given circuit, like when you guys do, the three things you find: the voltage gain, the input resistance, output resistance. Whether it's common source, whether it's common drain, common gate, or common base, common emitter, common collector. They're all we just for all kinds of circuits we do the three things. So once you find it, remember in the beginning of this section we talk about generic amplifiers. So now you have this can find you can draw the equivalent circuit of that is going to be like you have input resistance and you have a gain. Yeah, you have input resistance. Actually, if we do the voltage gain now, so because we have voltage gain, so actually, yeah. So the only thing that we have to be careful when we draw the equivalent circuit is how AV is calculated. If AV is calculated on VSIG, so therefore that AV already included VSIG in the equation. If AV is connected without SIG, so now you have to do a voltage divider. So just make sure that you guys understand these two circuits. There's a little bit difference over here. V pi. So that AV, let's call it AV1 here, AV2 does not equal to AV2. Because in the first one, our AV is calculated by using the ratio between VO and VSIG. But the second is calculated by dividing VO and V pi. So this is kind of the translating our amplifier. Usually we have a current source. Now we're converting them into actual a voltage source. And you can see clearly what the voltage gain. So, okay, so that's what we have. Maybe now if you connect like a load resistance, for example, if voltage 10 volts, your resistance 5K, your load 5K, now your output actually half of the voltage gain here. Now, if it's a current source over here, remember what we do is we have these two in parallel, which basically give you the same thing, because when they're in parallel, your resistance reduced by half, and your current is constant. So constant current times half volt resistance also give you half of the voltage. So exactly the same output. Okay. So this is a common gate. Now we're gonna move on to talk about common base. As I said before, this is almost identical. Almost identical. The only difference is here. See, the whole circuit configuration is the same. The base is grounded. The voltage and RC is connected to the emitter, and collector is connected to a voltage source, which in this small case, signal case, is a ground. Okay. So what you do is you go find the equivalent circuit, small signal equivalent circuit of the BJT, which we know here. And you guys know that for the BJT, the equivalent circuit, again, we're going to use T-model because every time, as I said, every time you find there's something connect at the emitter, if the emitter for small signal cannot be grounded or the source cannot be grounded for small signal, you always use T-model. That will make your life much simpler, much easier. So the T-model says that you have a current source over here. right? That's your T model. So you see, within that T model, what we did, we moved that T model over here under the blue background. That's your T model. In this T model, the top current, the two is to represent the current. One is called GM times V pi. Right, so okay, because the T model often we don't use voltage anymore because of the T model, it's easier to use current. So it's alpha times IE, and the bottom is IE, and the current in the base is IB. So that's the only difference between this one and the MOSFET model. The bottom is the same, the output is the same. Simply we use a different symbol RC instead of RD. Everything else is the same. So in this case, what we're going to do is we want to find also VO. We want to find R in. We want to find I out. Okay. So you know to find VO. So let's do it over here. So I'm going to redraw the circuit on here. All right. So that's the circuit. So if we look at the equivalent circuit, we can start by defining VO equal to minus RL times alpha times IE. Right? So alpha times IE is IC. RC is alpha times IE. So I use, yeah, it is IC, but IC, huh? Huh?
Or what?
RC. Matter of clarification. Yeah, this is RC. Yeah. So we have this. So the next step is try to find IE. Similar to the previous MOSFET, what you're going to do is look at this loop. This is ground, and this is ground, to this loop. So when you have this loop, you can find IE is going up, actually, right? So which means IE actually is negative, this voltage divided by this plus this. So we have IE so IE where I equal to minus VSIG over RE plus SIG. So we got IE. So now we got IE, and of course, step 3 will be simply plugging VO. So minus and cancel. We have VSIG over RE plus SIG times RC. So therefore, step 4, we get V equal to VO we have AV calculated. That is fairly simple. Let me see. Now we need to just one more thing is we need to find out what actually yeah, because this is RE equal to alpha over GM, right? RE is equal to, so RE is equal to alpha over GM, and sometimes just simply approximately equal to 1 over GM. This is a slight difference between MOSFET. When MOSFET RS is absolutely equal to 1 over GM, but in this case, alpha over GM, slight difference, like 99%. Yeah.
Where alpha go if the calculation is
What is it?
alpha?
Alpha.
Where did it go?
Yeah, that alpha. No, actually, you're right. We actually
Yeah, we need the alpha.
we need the alpha. Yeah, you're right. We need the alpha. Sorry about that. Sorry about that. Alpha is here. Okay. Yeah, we need that alpha. Thank you. So we can plug in RE back into the equation. So we can find AV. So that's what we do. And then next time we want to find RE in. So to find our input resistance, remember what we did in the MOSFET is we're going to ground the whole VISG and RSIG. So we have the circuit we're going to ground. Because now, once this ground, this forms an actual loop. So therefore, your II equal to VI over RE. So therefore, your RE equal to VI over II equal to just RE, which equal to alpha over GM. So it's approximately 1 over GM in the sense that for MOSFET, it is 1 over GM, but for this case, it's alpha over 1 over GM, the way we have. Let's see, if we have R out, you probably by this time you already figure out that I out is very simple because again, when we short the input, we apply voltage. I mean, we can still do the circuit, like we can still do the circuit over here. So you would short the circuit, you will short the ground. So therefore, IE equal to 0. Therefore, current is going to be open circuit. So therefore, your R out is equal to VO over IO, simply equal to RC. RC, okay? So common gate, common base, yeah.
Short input, so you're taking out VSig and you're putting in VI. So you can.
When you calculate input resistance, yeah, you take out VSG and put a V in over there, and just like a testing voltage, you know, like ideal voltage source, no internal resistance connected to final current. I mean, in real life, in the laboratory, let's say you give you a black box device, I want you to find the input resistance. What would you do? Find a voltage source, measure the current, and you'll find it. And the output side do the same thing, but of course you short the input. So that's only it. Yeah. So we find that. Now we can move on to look at emitter follower or source follower. Sometimes it is a very good question to ask in the beginning. What does a follower mean? Follower means the output follows the input. Like your input is 1, the output is nearly 1, or 999, 0.999. So, and then the question is that if input and output is the same, why would you do that? So this example really tells you why it's important. You know, the top circuit, like A, for example, if your input is 1 volt, but your internal resistance is 1 meg, and your input resistance is only 1K. how much would you get actually to be amplified? Only a small fraction, like less than 1%. What is it? 1/1000 is 0.1%. 99.9% is dropped on its internal resistance. So if I want to ask you a simple question for circuit A over here, you want to increase the percentage of voltage that gets amplified. What would you do? What are the things that you can do in this case? Yeah.
Well, what did we do?
Suppose those resistance, can be changed.
Make our internal resistance as small as possible. Or our signal resistance as low as possible.
Yeah. So what you need to do is that, like, look at circuit A. So there are two things that you can do. One is that you can reduce R-sig, if possible, right? If you reduce, let's say, R-sig to 1K, what happens? Now half of that gets to the load, right? So that's one thing you can do. But unfortunately, often, the signal resistance is not something that you can really do. So what do? You use like unit amplifier or voltage follower. That's what happened. Okay, another thing that you can do, you can increase RL. Right? If you increase RL to say 1 meg, what happens? Again, you get half of that voltage, right? So, so our job is to, okay, if I increase RL to like infinity open circuit, well, how much is the output? Same as input, right? So that you get 100% of those pass through. So that's why common, like MOSFET amplifier is important, because that gate is open for small signal equivalent circuit. So whatever the input resistance of the signal source, it doesn't matter, because the input resistance of the MOSFET is infinity, right? So yeah, so that's the circuit. So basically what this is doing, just calculate how much voltage you have. Like with 1 volt, you only get 1 millivolts, which really a bizarre situation. Well, you have 1 volt coming, you get only 1 millivolts output. That's not going to work. So by doing this unit gain amplifier, what this unit gain amplifier is unique about, okay, there's 3 things. The gain is approximately 1. So it's like unit gain. Second, the input resistance is very large. It could be just infinity, very large. Okay. So if this is very large, how large? Let's say, for example, if this is 10 meg, and this is 1 volt coming, how much is going to here? It's like 90%. If this is 100 meg, 99%. If it's 1 gig, 99.9% is applied at the input. So when this is very large, 1 volt, almost 1 volt applied here, which is good. And unit gain means the output over here is 1. Okay, input is 1 volt, output is 1 volt, because gain is 1. And the third property is output resistance is very small in comparison to your load resistance. Now, for example, in this example, they have output resistance to be 100 ohms. And your load resistance is 1K. Now, output is 1 volt. So 1 volt divided between 100 and 1K, you got almost 90%. Okay. Now, if I want to further increase this one, what do? I can increase the load resistance, let's say to 10K. Now I would get 99.9%. Or I can reduce this one further to 10 ohm, keeping 1K, but this 10 ohm. You got what? Also, again, 99% or more applied to load. So that's why unit gain amplifier is so important in our applications. It's almost like often that you have one unit gain amplifier at the input side and unit gain amplifier at the output side. And in the middle, you have like regular amplifier to give you a lot of gain. Like, okay, I have unit amplifier coming in, 1 volt, and I have output is 1 volt, but my output is very large. So the middle part, I have very large gain, like maybe say 5,000. Okay, and then I had another stage is unity gain amplifier because I decrease my output resistance. So that's how this works. So typically, like you have input coming in, and you have so this unity gain, this is like 100.
So it's just good for decreasing the output resistance. If that's what
Decrease the output resistance, increase the input resistance. Both. So this is very typical. Your input coming in. You have unity gain at the input side, you have unity gain at the output side, and you have a lot of gain in the middle. Like 100 times 100 gives you like 10,000 gains, very big. But of course, after this, often we have another stage called power amplifier, like Class A, Class B, Class C amplifiers that we also added. But here, like even for signal, that's how it works. So now we're going to move on to talk about how each of this is going to work. Okay. So first of all, we're going to look at this source follower. This side is our source follower. For the source follower or unity gain, we have the drain grounded. So often this is also called a common drain amplifier, common drain, because the drain is grounded, drain and the input share the ground, so it's a common drain. And the load side is connected to the source is grounded. So the load is between source and ground. So the actual circuit, we're going to move on to the next slide. So I have more space to draw. So the actual circuit often is going to look like this. Actually, I'm going to do this. So this is the actual amplified circuit with DC biasing. You have VDD to supply the biasing current or biasing voltage. And you have VO is gain at the source. So for the circuit like this, remember what we do is we find the small signal equivalent circuit of the MOSFET. In this case, I said, because there's something at the source. So what we're going to do, we use T-model. So we're going to use T-model. Okay, so that's very simple T-model. And now we're going to connect each component at each terminal. So for the drain, what we found is the drain is connected to ground because that's a DC voltage. And for gate, we have and then for source, we have so now we have the circuit. So what we're taking output is VO at over there. So if you look at this circuit, is we can find well, similar to the previous one, let's write down. So what we need to do is we need to find AV. We need to find all these three so that we can verify our claim that that this is going to tell us that the three things. So the three things says AV is equal to 1, and this is large, and this is small. So we're going to find these three solutions. So first of all, let's find AV. So by definition, our AV is going to be so one of the things that we need to find out is this sometimes it's just a little bit confusing, but one thing we need to be careful is even though the gate is connected to input voltage source, but remember there's no current flowing into the gate. That's a typical for MOSFET. So therefore, ID would flow all the way like from ID through 1/GM through RS. So that semicurrent flowing above gate and below gate, that's a semicurrent flowing in the branch because there's zero current. So you're going to find that IG is really 0. So ID equal to IS. So if that's the case, what do you think the voltage at, see, just to make sure I don't make any mistakes. All right, so the voltage, I want you to find out what is the voltage at the gate, VG.
Voltage at the gate is going to be our default signal because there's no current flowing.
Right, because there's no current, so VG is the same as VSIG. So this is very important, so VSIG. Okay, so if that's the case, can we find the current over here? Let's call it IS. So then we would be able to find IS. IS is going to be VG over 1/GM plus 1/S, correct? Because that VG at there. So therefore, as a next step, we want to find VO. Just again recap. Because VG, because there's no current into the gate, so therefore VG is equal to same as VSIG. And the current is going to be VG over 1/GM plus RS, those two in series. Once we find the current, we find VO. VO is going to be just IS times RS. So we find VO is going to be IS times RS. So now we can find the gain. AV is going to be VO over VSIG equal to RS divided by VSIG. VG. So here is VSIG over. So we're going to plug in that RS. VO is RS times IS is SIG will divide by on the other side. So it becomes 1 over GM. So we find the gain to be very simple. It's going to be just RS over RS plus 1 over GM. So now at this stage, we want to verify, is this going to be really near unity? Well, it is kind of true because RS typically is in the kilo ohms, like 5K, 10K. But GM, 1 over GM is typically in the hundreds or tens of hundreds of ohms. So if this 10K is 100, 10K and 100, their difference is going to be like 100. So which means this value is going to be 0.99. So which means, so RS kilo 1 over GM so I mean, it's not absolute 1, but it's approximately, as I said, 0.99 or 0.96. Between, I would say 0.95 and 0.999, depending on the circuit parameters. And often for MOSFET, that number could be very close to 1. Okay? So we got that. So now next step is we want to find the input and output resistance. So in order to do that, I'm going to redraw the small signal equivalent circuit. I'm going to do it together. So the input resistance, it's going to be like input with IG, because IG equal to 0. So RG is infinity. So that one is simple. But for output resistance, it takes a little bit of effort. Let's redraw the circuit so you guys can get a better understanding. But we have to short this one. For output resistance, we're going to short it. We're going to short this one as well. So this is our circuit to find R out. Okay, so we short the input, and we apply voltage at the output point. We measure the current, and we take the ratio. So in this case, if you look at the current coming in, so what happens is that this is ground and that is ground. So what is the relation between 1 over GM and RS? Can you guys figure out? So basically you have ground. So you can see that 1 over GM and RS are actually in parallel, right? So means I can calculate IO equal to VO over in parallel with RS. So therefore, out is going to be VO over IO equal to 1 over GM RS. So 1 over GM, particularly let's say 100 ohm, RS is 10K. So how much is R out? So 100 in parallel with 10K, that you really get roughly like 100 ohms. So in comparison to the previous amplifier, like the common gate or common source, remember the output resistance is typically RD, right? And which is 10K. Now in this case, we have reduced that to be 100K, 100 ohm and a 10K resistance in parallel, which is approximately 100 ohm, which is 99 ohms in this case. But is that a small number? Yes. In comparison to 10K, it's a much smaller number. It's almost 100 smaller. So we achieved all three goals. Gain is 1. Input resistance is very large. Open circuit in this case, input resistance is very large and output resistance is very small. So 100 ohms to be small, but sometimes you can bring this even down further, by doing the circuit design. For example, if this becomes 100K, now this one will stay really near 100 ohms. Now, if you design a GM which large GM, instead like 1 milliamp per volt, you design this to be, let's say, 100. So what happens? And this becomes 10 ohm, right? So it becomes a GM. So if your GM is bigger, the output resistance is smaller. So we can reduce that down to 10 ohm or even like 1 ohm, depending on how you design your GM. So this is a very interesting circuit, and it's very useful. It's very useful. So next, we're going to go to common collector. Now we already done the common drain. Now it should be fairly easy to do common collector. So what we're going to do is we would find the equivalent circuit of the small signal model. And now the collector is grounded. And the output is over here. Okay, they call it RL, so I'm going to call it RL. So this alpha over GM. And similarly, we want to find VO, or in that sense, we find AV, and then we find R in, and then we find I out. And in this case, we also conclude that this is 1, this is big, small. And we're going to verify that, okay? So first of all, if we find VO, so VO is going to be alpha times RL. So, not alpha, sorry, IE. What I'm doing. Because IE flows up down through that branch. So IE is VO is IE times RL. So the next is we need to find what is VSIG, because the ratio is between VO and VSIG. Now, of course, now you guys know that, see, this is a loop. This is a loop. Even though the loop has a different current, but that's the purpose of loop analysis. They can have different current in different branch, but you can still write the loop equation. So in this case, your loop equation will be VSIG equal to the voltage drop on RSIG and the voltage drop on alpha over GM and the voltage drop on RL. So we're going to have VSIG equal to IB times RSIG plus IE times alpha over GM plus IE times RL. So now, of course, we know that IB equal to what? So IB equal to IC over beta, and IC is alpha times IE divided by beta. Yeah. So we can plug in this back into the equation, upper equation over there, and then we can have VSIG equal to IB is alpha over beta times IE. Oh, let's do this. 1 over beta. 1 over beta IE
Where did the alpha go?
1 over alpha, yeah.
The beta alpha.
Alpha over beta, yeah. IE over RL. So we can find AV is going to be IE of course, in this case, R you would cancel. You would have just RL over alpha over beta. Now, this equation can be a little bit further simplified because alpha is approximately 1. So therefore, you can say, well, this is like 1 over GM plus RL and then plus R sig over beta. So not so much change. But the fact is that these numbers are going to be really small. See, so I'm going to use a block over here. So alpha is approximately 1. And RL is typically like a 10K. And 1 over GM is like 100. Or alpha over GM is 100, right? So, and alpha over beta is also going to be like 100. So therefore, your AV is approximately 1. The reason that, you see, this is important because alpha is approximately 1, but beta is 100. So whatever RSG coming in is divided by 100 already. So even if it's 1 mega ohm, it divided by 100, it gets 100 ohm. So that's why I say, it's about 100 ohm. And this is about 100 ohm, but this is 10K. So 10K in comparison to 200, it's very big. You have RL. So basically, this goes to approximately 1. So we found the first property. So AV is actually approximately 1. So the next step is really just to find the input and output resistance. So in order to find the input and output resistance, what we do is we apply a voltage. Like when we find the input resistance, we apply voltage over here. Okay. So when you apply voltage, So we have, okay, I'm just going to do it on this slide. So we have so to find R in, we simply find VI over II. You guys notice one important thing is that the voltage across these two resistors is same as input. So therefore, we can find the voltage across here. We call it IE. So IE equal to VI over alpha over GM. Oh, so this, I mean, there's no big difference, but for accuracy, oops, 1 over GM plus, plus RL. There's one mistake a lot of people quite, quite easy to make is that, oh, we find IE and we use VI over IE together. That's not true because IE is the current in this branch. There's a current flowing down from up branch. Therefore, it's not II. II is actually equal to, yeah, II equal to IB, which is equal to, IC over beta, which is alpha times IE over beta. So you need to plug in this one to here, and what you find is R in is going to be VI cancel, so you have II beta. So okay, so let's write down.
It'd be beta top alpha.
IE is okay. So IE. So let's do it this way. So 1 over GM plus RL times. No. Let's just do it really quick. So IB equal to alpha IE over beta. So this II. And then IE equal to VI over 1 over GM plus RL alpha over beta. So that's II. So our R in is VI over II equal to 1 over GM plus RL.
No.
Beta over alpha. So yes. So you see what happens is 1 over GM is a small number, but RL is a big number. And you use a bigger number times beta 100. So if this is 10K times 100, I gives you 1 meg. So even though this is BJT, the input resistance can be huge, okay? So one more step is you will do, you'll find output resistance. I mean, output resistance is you're gonna short the input. That's similar to what we did with, I'll take you guys 1 more minute. We're gonna finish this. So if you look at what we're doing is we short the gate or short the base. You apply a voltage over here. So similar to the MOSFET, you know that this IO is basically VO over 1 alpha over GM in parallel with RL, right? So your R out is simply just equal to RL in parallel with alpha over GM. Again, alpha over GM is a small number, 100 ohm. So RL is 10K, but alpha over GM is going to be like 100 ohm. So Y out is approximately 100 ohm. So we achieved all three goals: unit gain, very large input resistance, and very small output resistance. So that's what we do for the unit gain amplifiers. Okay, with that, we are right on time. Thank you. We'll see you next time. We have